Hi everyone. So today is the day 4 of the September LeetCoding challenge, and on this day we have been given to solve this problem, and this problem is sum of distances in tree. So in this problem, there is a tree, and we need to return the sum of distances of every node from a particular node. So we can take a look to an example. So here n is equal to 6, and the edges are given. So the answer output is 8, 12, 6, 10, 10 and 10. And here from the node 0, the distance from all other node, the sum of distances to the all other node is 8. That is why it is 8. So all other numbers are the distances of every node from all other nodes. And here like n is equal to 1 and there are no edges, so there is like sum of distances to other nodes is equal to 0, so that's why output is 0. And here n is equal to 2 and there is one edge between the node 0 and node 1. So for this node the distance to this node is 1, so it is 1, and for this node to the distance to this node is also 1, so that is why it is 1. So now we can take a look to the constraints. So here n is less than equal to 3 into 10 to the power 4, and the edges length is n minus 1 because it is a tree, and this each edge will contain two numbers, so obviously it will represent the two nodes being connected by that edge, and the value of the nodes will range from 0 to n minus 1. So it is not 1 based indexing, it is like 0 based indexing, and there is no self loops, right? So that's why AI is not equal to BI. So you can try to understand this problem. So first of all, let us understand how will we approach this problem. So the usual approach of calculating the sum of distances of every node for each node will take like a order n squared time, because for calculating the sum of every node for one node will take order n time, and since there are n nodes it will take order n squared time. So we need to do some optimization, and there is one very good trick for supporting this optimization. So let me explain. So suppose in the tree there are two nodes, and every this node has got its own subtree, and this node has got its own subtree, and these two nodes are connected with an edge, and I can call this node as A, and I can call the second node as B. And now the subtree of A and subtree of B, we know the sum of we know the sum of the distances of every node present in the subtree from this node A, and we can call that suppose say it is sum of A, and similarly it is sum of B. Now suppose we want to know the total sum of all the distances of every node in the tree from A, then what will how can we represent this sum in terms of the sum A and sum B. So if we observe, then we can see that the sum, total sum from A will be equal to sum of A, and sum of A will include the sum of all the nodes present in the subtree of A from this node. Now we need to add the sum of all the distances present in this subtree. So the distances of every node present in the subtree B from A would be sum of B plus count of B, where count of B is the number of nodes present in the subtree of B. So it is count of B because every node is one edge greater when every node, the distance of every node present in the subtree of B is one more than the distance from the node B. Suppose the distance of this node is 1 from this node B, then this distance will be this the distance of this node from A will be distance from node B plus 1. So it will be plus 1 for every node present in the subtree of B. So that's why I'm doing count of B, and count of B represent the number of nodes in the subtree of B. And similarly, the total sum of B will be sum of A plus count of A plus sum of B. So now we can represent total sum of A and total sum of B in terms of each other. So how we can do that? Because this sum of A plus sum of B is common in both the expressions. So we can replace the sum of A plus sum of B term by total sum B minus count of A. So this is now, so this total sum B minus count of A is equal to now this sum of A plus sum of B, and we can then so this is the expression. So if we know the total sum of node from any node, we can get the total sum to its adjacent node by just first subtracting the count of the node of which we want, plus adding the count of the a number of nodes in the present subtree. So this is one concept. So this concept will help us to find the sum for every node if we have got sum for one node. So getting a sum of distances for one node will take order n time, and using this expression we can find the every other sum in order one time if we know if we have already got this count A and count B, count of every subtree. So what we will be doing, we will be first calculating the count of every subtree and the total sum of one subtree. So basically if we will be rooting this tree, then this subtree sum for the root will actually be the total sum for the root. So we will be first calculating the subtree sum and count of every node present in the tree, and we will root the tree with node 0. So let us understand how we will be calculating the total sum of the root. So first it is this diagram. Now suppose this is the parent, this is one node, and these are its children. And these have, all of these have got their own subtrees, right? So suppose we want to know the sum of this, sum of the distances from this node, then like the sum of distances from every node from this node will actually be sum of A. Suppose I am saying it is A, it is B, it is C, and so on. So it will, the total sum will be sum from node will be sum of A subtree plus count of A, because every node present in the subtree of A is one edge more distant from this node, and plus sum of B plus count of B to include the sum of distances for every node present in the B, and so on for other nodes. So basically we can use a DFS, and we will call the DFS to like first calculate these two quantities, sum and count, for its subtrees and like for its children, and then we can add them in this order to get these quantities, sum and count, for the parent node. So let us try to implement. So first of all, we can erase this diagram because now we have got the expressions. So first of all, we will be making adjacency list. I'll be using a vector of vector, and I will call it ADJ, and we can have size n because all the nodes are having the values from 0 to n minus 1, and now we can consider every edge in the edges. Now we need to push S0 and S1 into vectors of each other to make the adjacency list. So now we have got the adjacency list. Now we will be having a vector for storing the count of nodes in each subtree. So I can initialize it with 1 because every subtree will have count 1 initially to include the the node with which it is having the like including the node which it is having as its root. So we will also have a vector for storing the sum of distances of all the nodes present in a particular subtree. So I can initialize it with 0, and now we need to calculate the sum of all the subtrees and count of all the subtrees. So I will be using DFS, and I will call it DFS root, because it will, after its execution, it will give us the total sum of the root. And this DFS root, and this DFS root will be a void function, and it will take a node, and it will take a parent, and then it will take int10. Then we need to pass the adjacency list so we can carry out this DFS thing. I'll be passing it by reference. And then we can have this sum. So we will be first iterating over all the child present in the adjacency list of the node, and if this child is not equal to parent. So the like main purpose of passing the parent is so that we can also only iterate, like consider all the real children nodes. So first we will need to call this same function for this child. So child, and the parent in this case will be the node, and then you can pass the n, and then edges. No, it is not edges, it is adjacency list. And then we will have the count and this sum. So after doing this, we will have access to the sum of this subtree and count of this subtree. So we know that the sum of the node will be, first let us calculate it. So the count of the node will be the sum of count of every child it has, and sum of node will be the sum of every child it has plus count of every child it has. So this thing will like calculate the sum and count for every subtree. So now we have got the total sum for the root, because the sum of the root is actually the total sum for the root. So now we can use that adjacent nodes expression to count the total sum for every root. So I will be like storing the total sum in this same sum vector. So I will be calling another. First let me call this function. So this function will be called with 0, -1. So for parent we can take any node other than, like if we are not taking any quantity ranging from 0 to n-1, it will be fine. So yeah, so 0, -1, then we will have n, then we will have our adjacency list, and then we will have count and sum. So I will be calling another DFS function, and I will call it DFS all, because after calling this function it will calculate the total sum for every node. It will be like, yeah, so the function signature will be same, as it, and we need to consider every child in the adjacency list of the node. So if the child is not parent, so we need to like complete this thing. So if like now we are considering every child of the node, so we know that the total sum of the child will be equal to sum of the node minus count of the child plus count of the node. So this is what we have from this expression, and since will be like moving downwards from the root node, we will have the sum of this node, and we already have the count of every child and every node, so that's not an issue. So we can like rewrite this count of node. So basically here like the count of node is, so in this expression like we were considering these two nodes with their own subtrees. So in this case it was not rooted, the tree was not rooted, so the count of node will be the n minus count of child, because every node that is not present in this child subtree will be present in the node subtree. So this is the expression, and we can write this as it is. Yeah, so the variables are okay, but only thing is that we need to write the count in this notation. So like this will calculate the sum of the child, and after calculating the sum of the child, we can again call this DFS. So this is not DFS root, this is DFS all. So we can again call this function DFS all for the child node. So this function will ensure that the total sum of every node is calculated, and yeah, so after calling these two functions, this sum will contain the total sum of every node, so we can return the sum now. We are getting runtime error, so like let us understand why we are getting. We are calling these things. There must be something here. So sorry, it should be 0 actually. Like I was doing 0 1, so in the flow I wrote 1 2, so it should be 0 1 and 1 0. So now like we can try again. Yeah, so it is working on the sample test case. We can submit it. Yeah, it got accepted. So thank you guys, see you again tomorrow with the new problem.